There are few diagrams given in the question. We have to identify out of these diagrams which all correctly represent the electric field lines. So this is one single question out of A, B, C, D. It find out which line satisfies the properties of electric field lines and represent the electric field lines correctly. And out of this A, B, C, D, which all diagrams show the correct representation of electric field lines. So we need to have an idea what is an electric field line and what are the basic properties of electric field lines. So electric field lines represent the path followed by a vanishingly small positive test charge if it is placed under the influence of another source charge or charge system. Source charge means the charge which produces the field. Test charge means the charge what we are introducing to understand the presence of the field. For example, this is a source charge which is held stationary, maybe positive. When you are introducing a test charge, positive test charge, by definition test charge is always positive, and the value of the test charge is supposed to be very small, approximately or close to 0, can't be 0, so that the test charge don't create a field which add up or subtract with the field of the source charge. So to reduce the influence of test charge on the field produced by the source charge, the test charge is always taken to be very close to 0. Its purpose is just to understand the field produced by the source charge. So the source charge is generally at rest. The test charge is one which tend to move away close under the field or force of the source charge. So both are positive, like charges repel. So this test charge will be repelled by the source charge. Go right. Instead, if you transfer the test charge to this point down, it will be repelled down. So this path followed by the test charge under the influence of a source charge or a group of charges called charge system. That is what you call electric field line. If the source charge is negative, still the test charge is always positive. So if you bring a positive test charge here, unlike charges attract and the source charge is at rest, so the test charge will be attracted towards the source charge. So if you bring the test charge somewhere at a different point above the source charge, will be again attracted towards the source charge. So the electric field lines are basically the path followed by a vanishingly small, close to 0, positive test charge under the influence of a source charge or a group of charges called charge system. That's a basic definition for an electric field line. Now we have to learn some properties. From the last diagram itself, it's clear. The direction of electric field line is outwards, away from a positive charge, and the direction of electric field or field lines are towards for a negative charge. That's one basic property of electric field line. That because a positive charge is always repelled by a source charge and a positive test charge is always attracted by a negative source charge. There is no other option. The field line has to be outwards for a positive source charge and towards for a negative source charge. So that's the reason. Now number 2, the electric field lines are always normal to the surface of a charge conductor for charges at rest. we deal with charges at rest in electrostatics, not charges in motion like current electricity. That may be a different case. For charges at rest, the electric field lines are always normal to the surface of a charged conductor. So the reason for that, if the electric charges are at rest in electrostatics, they should not move on the surface. If you have electric field lines not normal to the surface of a conductor, there will be a component of electric field which is parallel to the surface. For example, if you have a surface maybe a surface. So the electric field line is a conductor. The electric field has to be normal to the surface. That's a rule. If it's not normal, you can resolve this electric field into two components. So one component will be parallel to the surface, one component will be normal to the surface. So if you have a charge here, this charge plus or minus charge, because of this electric field, that will be forced to move on the surface of the conductor. So if this angle is theta, this component will be E cos theta. So the charge will experience a force F equal to Q times E, which is E cos theta. So the charge will move on the surface of the conductor. In electrostatics, charges should not move. So there will not be a component parallel to the surface only when the electric field lines are normal. That time the angle with the surface become 90 degree. So cos 90 will be 0. So this component will be 0. There should not be a component parallel to the surface for the charges to be at rest. So the electric field cannot be inclined to the surface, because inclined meaning there will be a component parallel. The field lines has to be normal to the surface of the conductor. That's why for all charged conductors, the electric field lines has to be normal to the surface of the conductor. Now electric field lines are absent inside a conductor. Inside a conductor, the electric field is 0. There are no charges inside a conductor. If you have a conductor, whether it's solid or hollow, even it is a solid conductor, conductor is allowing the charges to move. So even you give a charge on the conductor, whatever type of charge you give, they have mutual repulsion. The repellent go away, so that they stay only on the surface of the conductor. The charges always stay only on the surface of the conductor. There are no charges inside the conductor. Since charges are 0 inside, electric field is also 0. The electric field is 0, there won't be any force on the test charge. So if even you keep a test charge, the charge will not move. That means if electric field is 0, as the charge is 0, there won't be any force. So electric charges don't move inside the conductor. So electric field lines are absent inside a conductor. Basic reason is electric field is 0 because there are no charges inside the conductor. Charges stay only on the outer surface of the conductor in electrostatics. So E is 0 means there is no force on the test charge. The field lines are not there because the charges don't move. Now electric field lines do not intersect each other. Maybe grade 10 you might have learned magnetic field lines never intersect, because if they intersect at the point of intersection, there will be two directions possible for the magnetic field line. For a vector, at a point only one direction is only practically possible. The same way, if two electric field lines intersect at the point of intersection, there will be two directions possible for the electric field vector. For a vector, you cannot have two directions at a point. So it's against the basic rule. So they cannot intersect. Electric field lines cannot intersect each other. Another one, electric field lines are continuous curves without any break. There's no break for an electric field line. If there's a surface, there can be a break. Otherwise, wherever electric field is there, it cannot have a break. And it is not closed. The field line cannot form closed path. Meaning, if you draw an electric field line, it must be continuous like this. It cannot have sudden break in between. If there's a field, in a field, electric field lines has to be continuous, and electric field line cannot form closed path. This is wrong. An electric field line can move outwards or inwards, but it cannot form closed path. If you have an electric field, if this has an electric field region, and if you leave a test charge here, always the test charge experience a force F equal to Q. Since the charge is always present on the, since the force is always present on the test charge, the charge must be continuously moving, the path must be continuous. In a region of continuous field, the test charge always experiences a force and it always or continuously moves. So the path will be continuous. Now why it can't be closed? We take a positive source charge. This path is basically the movement of a positive test charge. A positive charge is only repelled by a positive source charge. It's never attracted. It can only go away from the source charge. It never can come back to the source charge because like charges never get attracted. So electric field lines cannot be closed. These are the important properties regarding the electric field line. This is for why it has to be continuous without any break, and this for why it has to be not closed. Electric field lines cannot be closed. So based on these properties, you have to go back to the question. This is a conductor, so it's not mentioned, but it's a conductor as per the question. So field line B and C are not possible because they are showing electric field line inside a conductor. We know electric field lines are absent inside a conductor. Since electric field lines are absent inside a conductor, out of this A, B, C, D, B and C are not correct. A is not correct because electric field lines are always normal to the surface. It has to be 90 degree with the surface. This is not making any 90 degree. It's like a acute angle. But the D, the line D, it comes, then at this point it becomes what? Normal. Even it comes out normal. So out of A, B, C, D, in this particular question, for this being a conductor, A, B, C are wrong. D is the correct representation. Now in the second part of the question, diagram A, here it's showing the electric field lines are intersecting. So this is not correct. Even it's showing the field lines are coming towards positive. So for being wrong, you can just one reason enough. So B is wrong because they are showing field lines as closed curves. Field lines can never be closed. C is also wrong for a conductor. Always the field lines has to be normal. There are some field lines which are normal, but this field line is not making normal. This is also not normal. So for a conductor, every field line has to be normal to the surface of conductor. So A is wrong, intersecting. B is wrong because there are closed paths which is not possible for electric field lines. C is wrong because the field lines are not normal to the conductor at every point. D represent a correct representation because it is a positive charge. If you leave a positive touch, it will be repelled away. This also positive, so it's repelling the test charge away. So D only can be the correct representation. There are additional properties, but these are the important properties for electric field line. Maybe one more property in uniform electric field, the field lines are parallel and equidistant. If you want to represent electric field lines as uniform field, the lines has to be parallel and equidistant. The gap between the lines has to be same. So this is one field line. So the second field line has to be parallel to that. Even the third and fourth, how many field lines we have? all these field lines have to be parallel. It cannot be like this. Now the gap is different. It's not uniform field. So if you draw all the field lines parallel and equal, this is called uniform field. Now another point, maybe we discuss the properties. The relative closeness of the field lines indicate the strength of the field. So meaning here the field lines are equally close everywhere. This is uniform field. But if you draw field lines which are close at some points and which are farther at some other points, like the gap is different for the field lines. Wherever the field lines are close, that indicates strong field, and wherever the field lines are further apart, that indicates a weak field. So this is a region of strong electric field, and this is a region of weak electric field. So these are the important properties of electric field lines. And we will discuss 5 properties for the question, which basically can be one topic for properties of electric field lines.